Hello my friends, and welcome to the Nature Channel, where today we've got a special treat in store for us. We've travelled to the distant land of Unit 6, where if we're lucky, we'll catch a rare glimpse of two species, the glorious exponent and its relative, the humble radical, in their natural habitat. While the two coexist in harmony, even the slightest of disruptions to the ecosystem may upset the balance, so you've got to be careful so as not to startle them. Oh look, there's a wild exponent now. Such a majestic creature. Oh no. I think it spotted me. Run! Oh Lord, it's caught me! Ah, not the face, not the face! Ah! Hi friends, how are you? Welcome to our first class of Unit 6, Operations with Exponents and Radicals. Now I'm being a little bit dramatic, as is often in my nature. Exponents and radicals aren't particularly deadly, but they might feel a little bit new. We're arriving at a point of what I like to think of as transition in our algebra curriculum, where we want to be able to bridge the gap between the stuff that we find in Algebra 1 and Algebra 2. And in order to do so, we need to know how to work with both exponents and radicals. The idea is that so far, almost everything that we've been working with, even the equations and expressions with multiple variables, have been linear, which of course means if I were to graph one, I would get a straight line, right? We know that from Unit 4. But there's a criteria that we place on all of the variables that we find in a linear expression or equation. They do technically have exponents, but they're invisible, which means that there's a hidden exponent of 1 next to every variable that we've been working with. But that won't always be the case. And from this point on, it in fact rarely will be. Moving forward, the types of equations that we'll want to solve are going to get a little bit more complicated, often because, like this friend over here on the left, they contain exponents greater than 1, like this 2 attached to my variable x. This is an example of an equation called a polynomial equation. You do not need to know yet what that word means. That's a Unit 7 problem, but we will learn how to solve this in Unit 7. This is, by the way, if you're interested, a particular type of polynomial equation called a quadratic equation. By definition, a quadratic equation, the biggest exponent that you will see attached to a variable is that friend 2. In this unit, we will in fact learn how to solve equations like this friend. The square root of x minus 2 is equal to 5. Now, the word radical is just a fancy mathematical word for a root, whether it's a square root, a cubed root, or a fourth root. So we're going to call this guy a radical equation. Not because its system of beliefs is particularly difficult or challenging for us to wrap our heads around, but because radical is just a fancy word for a root. But to know how to solve these, we need to first understand their anatomy, which means before anything else, we've got to get to know these funky little numbers that we call exponents, as well as their siblings, I call them, interchangeably called radicals or roots. Let's get started with exponents. So we know, back in Unit 0, we worked with exponents. This guy, 2 to the 5th, is one such example. And you may remember that we gave each of these things a name based on their position in the exponential expression. Well, here that 5 we know is the exponent, and you may remember that this guy 2 we called the base. Now the base, that's the thing that we raise to the exponent. It could be, in this case, a number, but it's often, we'll see in this unit, going to contain variables, or maybe even combinations of numbers and variables. And the exponent, of course, that's the thing that tells me, well, how many copies of the base do I need to multiply together? So 2 to the 5th, take 30 seconds, pause the video. What is that telling me to do? What does 2 to the 5th actually mean? Go! 5, 4, 3, 2, 1, and stop. Well, 2 to the 5th means I need 5 copies of 2 multiplying together. So this means 2 times 2 times 2 times 2 times 2. And it is, right, or it is equal to, well, 2 times 2 is 4, times another 2 gives me 8, then 16, and finally 32. Simplifying exponents like this is relatively straightforward. But the one place where exponents can get a little bit wonky is when it comes to negative numbers. So as soon as I throw in a negative sign, sometimes I might have a little bit of trouble simplifying. Try it on your own with 5 squared. Compare that to negative 5 in parentheses. So something in parentheses, we often say the quantity. So we'll say the quantity, negative 5 squared, and then negative 5 squared without the parentheses. Take a risk, take a chance, take 30 seconds, take a minute. How do you think the process of simplifying each of these expressions might look a little bit different? And the hint that I'll give you is you might want to think about order of operations in some way. Go ahead, pause the video, see what you come up with. Have fun. And let's come back together. Well, 5 squared by definition of an exponent, this means I need 2 copies of 5 multiplying together. 5 times 5 is equal to 25. Negative 5 in parentheses squared, or negative 5 quantity squared, we will say. Well, that means that the whole base, the whole thing being multiplied by itself is not just the 5, but the negative 5. So this, of course, means the whole thing in the parentheses, negative 5 times negative 5. Well, that would be negative times a negative, which is positive, and 5 times 5, which is 25. But for negative 5 squared, and you'll notice there's a difference in the way that I say it with a little bit of a pause between the negative and the 5. For negative 5 squared, the hint that I gave you was to think about your order of operations. This is really a PEMDAS problem in disguise. You may remember that a negative sign in front of something, that really means negative 1 times the thing. So negative 5 squared really means negative 1 times 5 squared. Well, here order of operations tells me that I should simplify the exponent first. So 5 squared gives me 25. Negative 1 times 25 gives me negative 25. So you'll notice the inclusion of those parentheses here changed the value of our expression from a positive to a negative, or vice versa. See if that same thing happens with something like this guy. 4 to the 3rd power versus the quantity, negative 4 cubed, versus negative 4 cubed. Take 30 seconds, pause the video, see if you notice the same thing happen. Go ahead. And stop. Well, 4 to the power of 3, that means 4 times 4 times 4. That, if you want, feel free to fact check me, is equal to 64. For negative 4 cubed, right, or negative 4 quantity cubed, well, that means that negative 4 is the base. So the whole thing, negative 4, is going to be multiplied by itself 3 times. So I have negative 4 times negative 4. Well, that's positive 16 times the negative 4 would bring me not to positive, but to negative 64. And here for negative 4 cubed, again, order of operations problem in disguise. This really means negative 1 times 4 cubed. Well, order of operations tells me that I should simplify the exponent first. So I have 4 cubed, which we found is 64. 64 times negative 1 gives me negative 64. This is, in fact, not a coincidence. The only thing that changes here is whether the exponent is odd, like 3, or even, like 2. Well, above, we noticed that if I took an even number as my exponent, if I took a negative base and raised it to an even power, something like negative 5 times negative 5, well, that would give me a pair of negative signs that would cancel each other out. We'll always be left with a positive output. But if I have an odd power, if I have 3 copies of a negative, 5 copies of a negative, 7 copies of a negative, there will always be a leftover straggler negative sign that will flip the value back to a negative number. Cool! This is in fact a pattern that will always hold. Nice! We're often most familiar with seeing exponents like 2 and 3 and 4 and 5 nice friendly whole numbers. But technically, any number can be an exponent. So, one last type of exponent that I'd like to introduce you to today, what if my number, it could be any number that I want, is a fraction? Something like 3 to the 1/2 power, or 8 to the power of 1/3. I want to figure out what this means. And in no world would I expect you to know or even to be able to guess what's going to happen here. So, in a rare turn of events, I'm going to tell you. We do not have the language yet to explain why. But if you're asking why, don't fret. We will have that language very, very soon. It turns out that fractional exponents, weirdly enough, they are a fancy way for us to write the other type of operation that we're interested in working with today. Every fractional exponent corresponds to a root or a radical. And the way that it works is that the denominator of the fraction tells me which root of the number I'm trying to take. So, 3 to the power of 1/2. I'm going to take that denominator of 2. It turns out that that 2 is going to become that little number here off to the side of our root, and then 3 is now the number that I want to find the second root of. But you may remember that we often don't bother to write this little number here of 2. We call this, more simply, the square root of 3, which we write as such. Same idea for 8 to the power of 1/3. Well, that little guy 3 in the denominator, it's going to become the little guy here, right outside of my root symbol. So 8 to the power of 1/3, the denominator of 3, tells me that what I'm actually doing is finding the third root, or the cube root of 8. Again, don't know why yet, just seeing that it is. And we will prove why in a future class. Don't you worry your pretty little head. Cool, so we know that every radical is technically, right, an exponent in disguise. That's why I call them siblings of each other. Let's talk a little bit more about roots and radicals. Every one that we see will look something like this. There will be some little number off to the left. We'll call it n, right? But it would be a specific thing like 2 or 3, as in the examples above. We'll always have that root or radical symbol. And then we'll have something inside of the radical. We'll call it a, right? And then a would be something specific like that 3 or that 8 up above. The way that we would say this statement, we would say that we are trying to find the nth root of a. So above, for example, the nth root of a, where n was 3 and a was 8, right up here, we would say that is the third root of 8, which we simplify to the cube root. Nice. Just like exponents, each of these little friends has a fancy name that we give them. Again, would not expect you to know it, but here's some good math terminology for you. This little friend n, that superscript up off to the left, we call this the index of a radical, whereas the thing inside of the radical symbol, you might expect it to be called a base because it's so much like an exponent, but radicals are fancy, so this guy has a fancy name too. Instead, we call it the radicand, R-A-D-I-C-A-N-D. So here, the radicand, just like the base, this is the thing that we're taking the root of. So we'll say that the radicand, we'll call it the quantity, because again, it could be a number, but it could also be a variable or a combination of numbers and variables. So it's just the thing whose root we're trying to find, or that we're trying to take. Whereas the index here, that little number off to the side, that's telling me which root I'm trying to take of the radicand. So this is which root of the radicand specifically we're looking for. The thing about working with radicals is that I often find it easiest to think of each one like a question in disguise. So I'm going to flip back up for a second. I want to think of the question that I should ask myself to make the process of simplifying a radical easier. Can you ask the square root of 3 as a question. Can you ask the cubed root of 8 as a question? What could I ask myself if I'm trying to find the value that is equivalent to this statement? Take 30 seconds, take a risk, take a chance. What do you think that question might be? Go. Five, four, three, two, one, and stop. So, if I want to find the square root of 3, the question that I might ask myself, this is asking me to find a number that multiplies by itself to get 3. For the cubed root of 8, I'm being asked what number multiplies by itself 3 times to get that value of 8. So in general, the question that we want to ask ourselves when we're simplifying a radical, the thing that we're interested in finding is the thing that multiplies by itself n times to get the radicand a. So as a question, we'll state it as follows. We want to know what number multiplies by itself n times whatever the specific index is to get a, whatever that specific radicand is. And this is such an important question, I'm going to star it, and then I'm going to star it again. Why not? Maybe I'll even give it 3 stars for effort. I love this question. It makes the process of simplifying radicals, at least for me, move way easier. Now that we know what we want to do, right, we're asking a question every time we're simplifying. Sometimes those questions won't always have nice answers, right? The square root of 3, there's no nice number that multiplies by itself to get 3. So this question doesn't have a particularly nice answer. How about negative 13 to the power of 1/3? First of all, take 5 seconds. Rewrite this as a radical for me. Go. 5, 4, 3, 2, 1. Very good. Well, I know from above that the denominator of the fraction tells me which root to take. So I'm trying to find the cubed root of negative 13. 13 is a prime number. There's no way that I can find a nice number that can multiply by itself 3 times to get 13, let alone negative 13. However, a lot of the radicals that we'll be asked to simplify, like the cubed root of 8 from above, these do have nice answers. Can you ask the cube root of 8 again as a question and then figure out what the value is that answers that question? Take 30 seconds, pause the video, and if you think you've got it, try it again with 81 to the power of 1/2. Go, go, go! And stop. The cubed root of 8. Again, I want to ask this as a question. This is saying what number multiplies by itself 3 times to get 8? Well, the answer to that question is 2. If I take 2 times 2 times 2, that will get me the 8 that I want. So the cubed root of 8 is 2. For 81 to the power of 1/2, again, first of all, I need to rewrite this as a radical. So the denominator of 2 tells me that I'm taking the second root, or the square root, of 81. As a question, this is asking me, what number multiplies by itself to get 81? Well, 9 times 9 is equal to 81, so that guy should work. The square root of 81 should be 9. But is 9 the only answer? Well, it turns out, no. If I were to take the negative version of 9, do you agree that negative 9 times negative 9 is also equal to positive 81? Well, the negative signs would cancel each other out. This would give me a true statement. So we have both a positive version and a negative version of a number that answer our question. Mathematicians noticed this, and they created a symbol to represent this idea. The symbol that we use to say that either positive or negative 9 would work is this guy. This symbol, literally a plus sign over a minus sign, unsurprisingly perhaps, we call this plus or minus. So whenever we take the square root, and it turns out the 4th root or the 6th root or any even root of a number, We always need to account for both the positive and the negative version working because the negative signs would cancel each other out and leave us with the positive number that we want. Cool. Now the thing about radicals, because they are exponents in disguise, negative numbers also give us some problems with radicals. So for example, try to simplify square root of 16 versus the square root of negative 16. Try to simplify the cubed root of 27 and the cubed root of negative 27. See what you notice here. Where is the wonkiness going to occur? Take a minute, pause the video, see how far you get. Go, go, go. Okay, well, the square root of 16, this would be 4 times 4, right? If I take 4 and multiply by itself, that gets me to 16. But it could also be negative 4 times negative 4. That works too. So our answer here, both the positive and the negative version, plus or minus 4, will do the trick. But for something like the square root of negative 16, well, I know that 4 times 4 gives me positive 16, so does negative 4 times negative 4. If I wanted negative 16, I need to do something like negative 4 times positive 4. But I need to multiply by the same number, right? It needs to be something times itself. Negative 4 and 4, those are different numbers. So it turns out that with the tool set that we have, it is actually impossible to find the square root of a negative number. So we say that the square root of a negative number does not exist. It is impossible to answer this question with the knowledge that we have right now. But does not exist takes a bit of time to write, so we'll abbreviate that as DNE. It turns out that the square root, the fourth root, the sixth root of any negative number, as long as we have an even root, it is in fact impossible to find an even root of a negative radicand. If the number inside the radical is negative and the index, that little number off to the side of the radical, is an even number, we can automatically say it does not exist. But for a cubed root of 27, well, positive 27, that's 3 times 3 times 3. So the cubed root of positive 27 is 3. But the cubed root of negative 27, well, if I take a negative 3 times a negative 3 times a negative 3, negative 3 times negative 3 gives me positive 9. Positive 9 times negative 3 gives me negative 27. So it turns out that I can find the cube root or the fifth root, the seventh root, the ninth root, any odd root of a negative radicand is okay. Fantastic! You now know everything that you need to know about exponents and radicals. If you would like a little bit more practice, I know the video is getting long, you can stick around with me and do some practice using the following examples. But if you feel like you've got a good handle on this, you are welcome to skip the remainder of this video. Hasta la vista, sayonara, I'll see you later. If you're still here, I'm assuming that you want a little bit more practice, so let's do some. I've got these 7 examples using what I've just learned about exponents and radicals. I want to simplify each expression. Take 2 minutes, pause the video, see how far you get, and then come back and check with me. Go, go, go. All right, let's do it. Negative 3 to the power of 3. Well, this, of course, means, right, the whole base is negative 3. So this means negative 3 times negative 3 times negative 3. Negative 3 times negative 3 gives me positive 9. And then I have positive 9 times negative 3. This is negative 27. And that tracks with the observation that we made above, that if we take a negative base and raise it to an odd power, we should get a negative value. For the square root of 144, again, this could be either positive 12 times positive 12 or negative 12 times negative 12. Both versions of 12 work. So we would say that plus or minus 12 is our answer to this question. Negative 11 squared. This is an order of operations question in disguise. This really means, of course, negative 1 times 11 squared. PEMDAS tells me I'd simplify the exponent first. 11 times 11 gives me 121. And then negative 1 times positive 121 gives me negative 121. For negative, cubed root of negative 125? Well, the cubed root of negative 125 I can work with. So this is negative, and then I have negative 125. Well, that is negative 5 times negative 5 times negative 5. So negative 5 is a number that multiplies by itself 3 times to get 3. Let me even write this using my order of operations. A negative sign in front of something means negative 1 times the thing. So negative cubed root of negative 125 means negative 1 times the cubed root of negative 125, which we've just shown is negative 5. And now I have negative 1 times negative 5. Well, that gives me positive 5. The fourth root of 1. Well, I have an even power, or an even index, I should say, right? And I'm taking the root of a positive number. So I could do, if I'm trying to find a number that multiplies by itself 4 times to get positive 1, well, that could be positive 1 times positive 1 times positive 1 times positive 1. It could also be negative 1 times negative 1 times negative 1 times negative 1. Notice that each pair of negatives is going to cancel the other negative sign out. I'll be left with a positive value either way. So it turns out that both positive and negative 1 will do the trick for us. For negative 2 quantity, 6th power, what this, of course, means, well, I have 6 copies of negative 2. So I have negative 2 times 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 negative 2. Again, we'll notice, right? Each pair of negatives, those negative signs are going to cancel out. So I'll be left with 2 times 2 times 2 times 2 times 2 times 2. Well, I've got 6 2's in total when I multiply them all together. That should give me positive here, 64. And for the 8th root of negative 64, I could see that 64 is some number of copies of something, but I immediately see that there is an even number outside of the square root symbol, or in this case, the 8th root symbol, and a negative number inside of that radical. As soon as I see an even index with a negative radicand, I know that my answer does not exist.